Okay, then let's start with electromagnetic induction. That is class 12, chapter 6 of physics. Chapter 6, electromagnetic induction. Introduction to the chapter. Electricity and magnetism were considered separate and unrelated phenomena for a long time. In the early decades of the 19th century, experiments on electric current by Oersted, Ampere, and a few others established the fact that electricity and magnetism are interrelated. We have already know in the past times, in the old times, it was thought that electricity and magnetism were two separate topics. They thought they were completely different branches. But after the 19th century, like the during the 19th century, the experiments conducted by Oersted, the Ampere, and a few others scientists established the fact that electricity and magnetism are related. They are not separate branches, but they are interrelated. They found that moving electric charges produce magnetic fields. Okay, for example, an electric current deflects a magnetic compass needle placed in its vicinity. This is what Oersted's famous experiment. This naturally raises the question, like, is the converse effect possible? We know that when electric charges are moving or a current is passing through a wire, there is a deflection or a magnetic field produced. So, the converse effect of this is the opposite possible? Like, is a magnetic field able to produce a current? Let's see. Can moving magnets produce electric currents? There's a question, and obviously they can under some rules. That is why we are reading this chapter. Does the nature permit such a relation between electricity and magnetism? The answer is a resounding yes. The experiments of Michael Faraday in England and Joseph Henry in USA, conducted around 1830, that is the 19th century, demonstrated conclusively that electric currents were induced in closed coils when subjected to changing magnetic fields. Okay, there were two scientists mentioned here. Those are Michael Faraday, is from England, and Joseph Henry, that he is from USA. They conducted experiments around the early 19th century and demonstrated that electric currents were induced in coils when subjected to changing magnetic fields. When there is a changing magnetic field, electric current was induced or created in the coil. In this chapter, we will study the phenomena associated with changing magnetic fields and understand the underlying principles. The phenomena in which electric current is generated by varying magnetic fields is appropriately called as electromagnetic induction. The phenomena where electric current is generated by varying magnetic fields, this phenomena is called as electromagnetic induction. That is the chapter name. When Faraday first made public his discovery that the relative motion between a bar magnet and a wire loop produced a small current in the latter. He was asked, "What is the use for this?" His reply was, "What is the use of a newborn baby?" The phenomenon of electromagnetic induction is not merely a of theoretical or academic interest, but also of practical utility. Well, let's read that again. When Faraday first made public his discovery was that relative motion, when we create a changing magnetic field between a bar magnet, I mean through a bar magnet with respect to a wire loop, Then small current is induced in the wire loop. That is his discovery. And there is a something written here that when he was asked that what is the use for this magnetic field creating electric currents, he replied that what is the use of a newborn baby? This phenomenon, okay, the phenomenon of electromagnetic induction is not merely of theoretical or academic interest. It's not mainly useful in anything, but it is also used in everything, but also of practical utility. Imagine a world where there is no electricity, no electric lights, no trains, no telephones, and no personal computers. Very hard to imagine and very hard to live in. The pioneering experiments of Faraday and Henry have led directly to the discovery of modern day generators and transformers. Today's civilization owes its progress to a great extent to the discovery of electromagnetic induction. Some of the applications of the this electricity and magnetic fields have been given, that is generators, and transformers. Now, there is something given about Joseph Henry here. Let's just read it. Joseph Henry, 1797, 1878, American experimental physicist, professor at Princeton University, and first director of the Smithsonian Institution. He made important improvements in electromagnets by winding coils of insulated wire around iron pole pieces and invented an electromagnetic motor and a new efficient telegraph. He discovered self-induction and investigated how currents in one circuit induce current in another. The next heading: Experiments of Faraday and Henry. The discovery and understanding of electromagnetic induction are based on a long series of experiments carried out by Faraday and Henry. The discovery and understanding of long series of experiments. We shall now describe some of these experiments. Let's see the experiments. Experiment 6.1. Figure 6.1 shows a coil C1. Let's see the figure first. Figure 6.1. Here, when the bar magnet is pushed towards the coil, the pointer in the galvanometer G deflects. This is a coil. This is a wire coil. It is connected to a galvanometer. It is basically a circuit. There is no battery here, only a galvanometer. And when this bar magnet here is pushed towards when it is pushed towards this wire coil, there is a deflection that is shown in the galvanometer. This figure shows a coil C1. This is a coil C1 connected to a galvanometer G when the north pole of a bar magnet is pushed towards the coil. A coil connected to a galvanometer G when the north pole of the bar magnet is pushed towards the coil. The pointer in the galvanometer deflects, indicating the presence of electric current in the coil. Okay, the deflection lasts as long as the bar magnet is in motion. As long as we move the bar magnet, we see a deflection. If it stops, the deflection also stops. Meaning deflection meaning the current or the EMF induced. The galvanometer does not show any deflection when the magnet is held stationary. When the magnet is not moving, there is no deflection at all. When the magnet is pulled away from the coil, When the magnet is pulled away from the coil, the galvanometer shows deflection in the opposite direction. If when the magnet was going this direction, the current or maybe the galvanometer showed deflection as shown here in this direction, let's assume. But if the magnet was moving away this way, then same amount of deflection the galvanometer would show in this direction, same magnitude but opposite direction. Meaning when the bar magnet was coming this side like this, let's assume the current was this side as shown in the figure, but when it's moving away the current will be opposite. Okay, magnet is held stationary, there is no deflection. When the magnet is pulled away from the coil, the galvanometer shows deflection in the opposite direction, which indicates a reversal of the current's direction. Moreover, when the south pole of the bar magnet is moved towards or away from the coil, the deflection of the galvanometer are opposite to that observed with the north pole for similar movements. Okay, what they said here is, let's assume the bar magnet was not north and south, it was south and north, and we are moving the bar magnet like this. Then the figure shows if it was north here instead of south, the figure shows the current is this side. But we switch the direction of the magnet. It is south this side now. It is moving like this. And the current will not be this side, but this side. And the galvanometer deflection will not be this side, but this side. And similarly, when we move the this south north magnet away, then it will show similar this way, and the galvanometer deflection will be this way. Further, the deflection and hence current is found to be larger when the magnet is pushed towards or pulled away from the magnet faster. When we move this magnet slowly towards the coil, the deflection shown in the galvanometer, the magnitude is less, meaning there is less current created. But if you do this very fast, then the deflection created, the amount of current induced will also be very large. Instead, when the bar magnet is held at a fixed and the coil C1 is moved towards or away from the magnet, the same effects are observed. Okay, let's, instead of moving the bar magnet, let's fix the bar magnet and move the coil. This coil will move this side and again come back, but the deflection will still show the same. It doesn't matter which you move, there will still be an induced current inside the coil. That is what's happening, what they're saying. It shows that it is the relative motion between the magnet and the coil that is responsible for the induction of electric current in the coil. It doesn't matter which you move, whenever there is a relative motion with respect to each other, there is motion, only then will there be a current induced inside the coil. That is the meaning. Okay, next experiment. Okay, let's see the next experiment here. Okay, current is induced in coil 1 due to motion of the current carrying coil 2. Current is induced in coil 1 due to the motion of current carrying coil 2. Okay, we know that from the prior chapters, we know that a current carrying loop will produce magnetic fields. So, a current carrying loop can act as a bar magnet. That is also something we learned. And here, if we see, instead of a bar magnet, we take a current carrying loop. As we know it will act as a bar magnet, this current carrying loop will also produce magnetic field lines. or magnetic field. And the same way, when we moved a magnet with a relative motion, there is a current induced in this circuit. The same way, how the bar magnet induced current in the circuit when it moved, the same way when this current carrying coil is in relative motion with respect to the galvanometer coil, there will be a deflection in the galvanometer. That is what the second experiment is about. It doesn't only depend on the bar magnet. What they're trying to say here is, based on the two experiments, what is creating or inducing the current in the galvanometer coil is neither the bar magnet nor the coil, but the changing magnetic field lines. That is what we can interpret from these two experiments. Let's see the second experiment fully. Experiment 6.2. In the figure we saw down below, the bar magnet is replaced by a second coil, that is C2, connected to a battery. The steady current in the coil C2 produces a steady magnetic field. As a coil C2 is moved towards a coil C1, the galvanometer shows a deflection, as I said before, similar to how a bar magnet will moving towards the coil will create a deflection. This coil C2, which is current carrying coil, will also produce a deflection. This indicates that electric current is induced in the coil C1. When C2 is moved away, the galvanometer shows a deflection once again, but this time in the opposite direction. The deflection lasts as long as coil C2 is in motion. As I said, in the magnet case as well, in this case as well, as long as the coils or magnet is in motion or in relative motion, there will always be EMF induced in the galvanometer coil or current induced in the galvanometer coil. When the coil C2 is held fixed and C1 is moved, the same effects are observed. Here, if we hold down this battery current carrying coil and move the galvanometer towards and away from this current carrying coil, the same thing is observed. It is the relative motion here as well. It is a relative motion between the coils that induces the electric current. Relative motion, the motion with respect to each other, which induces the the electric current. Now, experiment 6.3, the next experiment. The above two experiments involved a relative motion between a magnet and a coil and between two coils, respectively. Through another experiment, Faraday showed that this relative motion is not an absolute requirement. Figure 6.3, the below figure shows two coils, C1 and C2, held stationary. Coil C1 is connected to galvanometer G, while the second coil C2 is connected to a battery through a tapping key. Okay, let's see the experiment before. This is one coil, there is a key. This is another galvanometer, this is a galvanometer coil to where the current is induced, and this is a normal coil. This is also fixed. Both are fixed this time. It is observed that the galvanometer shows a momentary deflection when the tapping key is pressed. The pointer in the galvanometer returns to zero immediately. If the key is held pressed continuously, there is no deflection in the galvanometer. When the key is released, a momentary deflection is observed again, but in the opposite direction. It is also observed that the deflection increases dramatically when an iron rod is inserted in the coils along their axis. Okay, basically what we observed from the prior experiment, when there is relative motion between the magnetic field producing magnet and the current carrying coil, the magnetic field producing current carrying coil and magnet, and a galvanometer coil. Between these two, if there is relative motion, there is a current induced in the galvanometer coil, and the galvanometer coil is showing a deflection. But from his third experiment, Faraday proved there is no necessity for relative motion. There is no, like, this current induced is not due to the relative motion. The motion is not the one responsible for creating the induced current, but it was the change in magnetic flux. Here, if we see, these are two fixed coils, and here there is a switch or a plug key, and as long as we when we turn this switch on, there will be current passing through this coil, and there is a magnetic field generated, due to which there is a momentary small deflection in the galvanometer. But after some time, after instantaneously or after a fraction of a second, the galvanometer again resets. Just the time after we press the plug key, the galvanometer will show a deflection and come back to its original position. But after it is on, it won't show deflection. This coil, after it is on and we turn off this key, at that exact moment, there will be a deflection in the galvanometer. This as well, after some time, will come back to original. What we can observe or understand from this is, when there is a sudden implementation of magnetic field, when we turn on the current, a magnetic field is generated. At that time, there is a deflection in the galvanometer, and as the magnetic field, even though it is staying after the current carrying coil is still producing magnetic field, but then there is no deflection, meaning magnetic field, simply a magnetic field present will not create a current. Okay, then what about if we turn off the key? There is again a deflection, but in the opposite direction, meaning when the magnetic field suddenly increases, suddenly appears, and suddenly disappears, there is a deflection shown in the galvanometer. When magnetic field appears and disappears, at that time a current is induced. That is what we can understand. And when we place a iron rod, which is a ferromagnetic substance, in between the coil, then the deflection, the current produced in the galvanometer is observed to be higher than before. Why that is the case? The higher the when there is a iron rod placed here, the magnetic field is amplified due to the individual alignment of the domains that we have learned in the previous chapter. So higher the magnetic field, uh, the stronger the induction, the magnetic induction, higher the current induced here. But that does not depend on the constant effect of the magnetic field. It should appear and disappear. But in the prior case, if we observe, in the first experiment, when there is a magnet, it is moving and going away. It's not that the magnetic field is disappearing and turning on. It's not turning on and off. So that means it is the turning and off and on of the magnetic field is also not directly responsible for the induction of the electric current. So from all these experiments, Faraday concluded that when there is a change in magnetic field through this coil, with respect to this coil, when there is a change in magnetic field, not magnetic field but change in magnetic field with respect to this coil, only then will there be a current induced. And this more accurately we can mention it as magnetic flux, a change in magnetic flux which induces the current. Okay, the next topic is magnetic flux. Magnetic flux, Faraday's great insight lay in discovering a simple mathematical relation to explain the series of experiments he carried out an electromagnetic induction. Okay, the Faraday's great insight in discovering a simple mathematical relation. There is a mathematical relation which he discovered, which explained his discoveries on the series of experiments he had carried out, that is on electromagnetic induction. However, before we state and appreciate his laws, we must get familiar with the notion of magnetic flux. Magnetic flux is defined in the same way as electric flux in chapter 1. Magnetic flux through a plane of area A placed in a uniform magnetic field B can be written as phi B, which is equals to B dot A or BA cos theta. Magnetic flux is similar to electric flux. Magnetic flux is a number of field lines, the magnetic field lines passing normally through a cross sectional area. And this formula as well, it is very same, except in the electric field place we wrote as magnetic field, that is B. So it is B dot A, the scalar product of B and A, because phi B, the magnetic flux, is a scalar quantity. This is the figure, a plane of surface area A placed in a uniform magnetic field B, where theta is the angle between the magnetic field and the area vector. The notion of the area as a vector has been discussed earlier in chapter 1. Equation 6.1, this equation is the main formula for magnetic flux, can be extended to curved surfaces and non-uniform fields. We can use this formula even for curved surfaces and non-uniform fields. If the magnetic field has different magnitudes and directions at various parts of the surface as shown in figure 6.5, then the magnetic flux through the surface is given by the individual sum of the small area times the small magnetic field. Basically, this is the surface magnetic field. So this is a surface. This is a very arbitrary surface, a common surface. It's not a specific shape. It's not spherical. It's not square. It is a random shape. And in this random shape, at this point, a specific amount of magnetic field is passing through, and this point another specific different amount of magnetic field is passing through. So for us to calculate the total magnetic flux through this surface, we take a small area, that is ds, and calculate the magnetic flux there, magnetic field there, and integrate and individually summate we sum all the individual areas with their unique magnetic fields. Then we will get the total magnetic flux, where all stands for summation over all the area elements comprising the surface, and Bi is the magnetic field at the center at the area element DAI. The SI unit of magnetic flux is Weber or Tesla meter square. Tesla meter squared or Weber. Tesla is the unit of magnetic field. Weber is the unit of magnetic flux. Magnetic flux is a scalar quantity. That's why I use scalar product above here. That is B dot A. Now let's go to the next topic, that is Faraday's law of induction. Faraday's law of induction. From the experimental observations, Faraday arrived at a conclusion that an EMF, electromotive force or potential difference, or current, it's not directly current, but current is induced in a coil when magnetic flux through the coil changes with time. The conclusion, based on his many experiments, he came up with a conclusion that it is the change in magnetic flux with respect to time is what causes the induction of electricity or current in the circuit. Faraday arrived at the conclusion that an EMF is induced in a coil when magnetic flux through the coil changes with time. Experimental observations discussed in section 6.2 experiment coil explained you is using this concept. We can explain why the coil is getting a deflection or showing a deflection based on this conclusion, that because there is a changing magnetic flux. If we observe here in the coil experiment or the magnetic field experiment, only when there is a magnet, when there is a change in flux, when it's moving, it's not stationary, at that time the flux keeps increasing. Because of that, there is a change in flux. Because of that, an electric current is induced, and when it is moving back, again a flux is induced. I mean, the magnetic field is keep on reducing, meaning the flux keeps decreasing and changing. Because of that, current is induced once more. Same in this case as well. In this case, when the switch was on, magnetic field was generated and the flux rapidly increased from 0 to total flux. And when the switch was off, the flux from the total flux became 0 as it changed. Because of that, the current was induced. And when we observed that the faster the relative movement between each other, the higher the EMF induced. Because of that, he came to a conclusion that the EMF induced is directly proportional to the change in magnetic flux with respect to time. The faster the movement, the higher the EMF induced. The motion of a magnet towards or away from the coil C1 in experiment 6.1 and moving a current carrying coil C2 towards or away from the coil C1 in experiment 6.2 change the magnetic flux associated with the coil C1. The change in magnetic flux induces electromotive force in coil C1. It was this induced EMF or potential which caused electric current to flow in the current carrying, I mean in the coil C1 and through the galvanometer, meaning it showed a deflection. A plausible explanation for the observation of experiment 6.3 is as follows. When the tapping key K is pressed for experiment, the most plausible explanation for observation in the experiment 6.3 here. When tapping the key K is pressed, the current in coil C2 and the resulting magnetic field rises from 0 to a maximum value in a short time. Consequently, the magnetic flux through the neighboring coil C1 also increases, meaning there is a change in flux. It is the change in magnetic flux through the coil C1, the first coil, that produces an induced EMF in that same coil. When the key is held pressed, current in the coil C2 is constant. Therefore, there is no change in the magnetic flux through coil C1, and the current in the coil C1 drops to 0. When the key is released, the current in C2 and the resulting magnetic field decreases from the maximum value to 0 in a short time. This results in a decrease in magnetic flux through coil C1 and hence again induces an electric current in coil C1. The common point in all these observations is that the time rate of change of magnetic flux through a circuit induces an EMF in it. Let's read the common point. In all the three experiments, the the common observation is that the time rate of change of magnetic flux with respect to time through a circuit induces EMF in it. Faraday stated experimental observation in the form of law called as Faraday's law of electromagnetic induction. The law is stated below. The magnitude of the induced EMF in a circuit is equal to the rate of change of magnetic flux through the circuit. This is Faraday's law. That is, the magnitude of the induced EMF in a circuit is equal to the time rate of change of magnetic flux through the circuit. Mathematically, the induced EMF is given by E is equals to minus d phi b, that is change in flux, small change in flux by small change in time. The negative sign, why we use the negative, is because the negative sign indicates the direction of E and hence the direction of current in a closed loop. This will be discussed in detail in the next section. In the case of a closely wound coil of n turns, change of flux associated with each turn is the same. Therefore, the expression for total induced EMF is given by minus n d phi b dt. As the if the coil carrying the galvanometer is wound in many turns, each turn will have the same change in flux. So because of that, we can just introduce n here, and for the total circuit, the galvanometer circuit having n turns, the induced magnetic flux is directly proportional to the number of turns. The induced EMF can be increased or by increasing the number of turns of a closed coil. From equation 6.1 and 6.2, we see that flux can be varied by changing any one or more terms B, comma A, magnetic field and area, and theta, the angle between area and the magnetic field. In experiment 6.1 and 6.2, in section 6.2, the flux is changed by varying magnetic field. The flux can also be altered by changing the shape of the coil, that is by shrinking it or stretching it in a magnetic field, or rotating a coil in a magnetic field such that the angle between B and A changes. In these cases too, an EMF is induced in the respective coils. An EMF is not only induced when there is change in magnetic flux, it is actually only the change in magnetic flux, and this can be affected not only through the magnetic field and area vector, but it can also be altered. I mean, it can also be increased or decreased, the EMF induced, by changing the shape. By changing the shape, we decrease or increase the magnitude of area, so that is technically changing the flux. And by increasing the turns, as we know, EMF is directly proportional to the number of turns, and we can rotate it, then there is a change in the angle between them. So therefore the flux changes again. Okay, let's see the example here. Example 6.1. Consider experiment 6.2. A. What would you do to obtain a large deflection of the galvanometer? 6.2 is the coil experiment. How would you demonstrate the presence of an induced current in the absence of a galvanometer? Okay, let's see the question again. First question A. What would you do in the coil experiment to obtain a large deflection of the galvanometer? One thing we can do, that is move the second coil very fast. Next thing we can do, that is increase the current in the first coil, so the magnetic field is increased and the change in flux is large, or increase the turn in the first coil as well. Okay, let's see the solution. To obtain a large deflection, one or more of the following steps can be taken. First one, use a rod of soft iron inside the coil C2 to increase the magnetic field. It can not only be increased by increasing the current but also by adding the ferromagnetic substances. Second, connect the coil to a powerful battery. Third, move the arrangement rapidly towards the test coil C1. Okay, now second question B. How would you demonstrate the presence of an induced current in the absence of a galvanometer? We can do that by making it a bulb or anything like that. It will, when there is a current, the bulb will glow. If there is no current, the bulb will not glow. But if the current is very very small, there is a chance that the electricity power required for the bulb is not sufficient, therefore it might not glow. So therefore a very sensitive galvanometer is required to see very small amounts of current produced or generated. Let's see the solution. Replace the galvanometer by a small bulb, as I said, the kind one finds in a small torchlight. Why they said in a small torchlight? Because we don't need very powerful bulbs. Because if they were very powerful, the small currents won't be able to detect them. I mean, won't be able to like turn them on. The relative motion between the two coils will cause the bulb to glow and thus demonstrate the presence of an induced current. In experimental physics, one must learn to innovate. Michael Faraday, who is ranked as one of the best experimentalists ever, was legendary for his innovative skills. That's great to hear. And there was something given here about Michael Faraday. Let's read it. Michael Faraday, 1791 to 1867. Faraday made numerous contributions to science: the discovery of electromagnetic induction, the laws of electrolysis, benzene, and the fact that the plane of polarization is rotated in an electric field. Is also created with the invention of the electric motor, the electric generator, and the transformer. Is widely regarded as the greatest experimental scientist of the 19th century. Okay, that was his introduction, or that was his small paragraph given about him. Now let's see. Example 6.2, it seems to be a numerical. Let's just read it out. A square loop of side 10 centimeter and resistance 0.5 ohm is placed vertically in the east-west plane. A uniform magnetic field of 0.10 Tesla is set up across the plane in the northeast direction. The magnetic field is decreased to zero in zero point 0.7 seconds at a steady rate. Determine the magnitudes of induced EMF and current during this time interval. Okay, they gave it as a square loop. They gave side is 10 centimeter. With this we can find the magnitude of the area vector, and they gave or area magnitude of the area and resistance as 0.5 ohm, through which we can maybe find the EMF induced or the current passing through. They gave the magnetic field, which is essential for finding out the change in magnetic flux. The magnetic field from zero point 0.1 is decreased from that zero point 0.1 Tesla to 0, that is steady rate, uniformly in a time interval of 0.7 seconds. Okay, now they are asking magnitude of induced EMF, that is potential difference, and current during this time interval. And they give directions north, east, east, because we need to find the theta angle by the area vector. The angle theta made by the area vector of the coil with the magnetic field is 45 degrees, because maybe let's check the question more to see. Is placed vertically, meaning it is kind of hanging in the east-west plane. If this was a compass, north, east, south, and west, and they said that is placed vertically in east-west plane, vertically in east-west plane, meaning maybe like this. The magnetic field is decreased is zero. Okay, wait. And a magnetic field is set up in the northeast direction, meaning in this direction, and this angle with the area vector should be around like this. Since area vector is perpendicular to the surface, this angle between the magnetic field and area vector is said to be 45 degrees. Okay, they got the area vector of the coil with the magnetic field is 45 degrees, and flux, which is equals to initial flux, we are calculating here, and substituting the values. B, which is equals to 0.1, area, which is equals to 10 power minus 2 meter square, and cos 45 degree is 1 by root 2. Final flux is 0. Using the formula of Faraday's law, we will get the final EMF to be 1 millivolt, to be approximately equal to 1 millivolt. And the magnitude of the current, which is equals to E by R, this is Ohm's law, which is equals to 2 milliampere. Note that the Earth's magnetic field also produces a flux through the loop, but it is steady field which does not change within time or span of time, and hence does not induce any EMF. There is also Earth's field, but since it's steady and does not change with respect to time, does not induce a current within the coil. Next example, a circular coil of radius 10 centimeters through which we can calculate the area of the loop, that is pi r square, and it has 500 turns. We know that the EMF induced is directly proportional to the number of turns. There is also a substitution in the formula. Resistance is 2 ohm to find out the current when we found out the EMF. Is placed with its plane perpendicular to the horizontal component of the Earth's magnetic field. Okay, its plane is perpendicular to the horizontal component of the Earth's magnetic field, meaning it's the angle between the area vector and the Earth's magnetic field, the horizontal magnetic field, is 0 degrees. When the plane is perpendicular to the Earth's horizontal field, that means the area vector which is perpendicular to the plane is also perpendicular to the plane through 180 degrees in 0.25 seconds. Okay, we rotate this plane we rotate this coil about its vertical diameter, meaning if this was Earth's surface, the coil is placed something like this, area vector is this way, horizontal component BH, which is also this way, and this is the vertical diameter. This is not a rectangular coil but a circular coil. It is rotated about its vertical diameter through 180 degrees in 0.25 seconds. It is rotated like this, meaning what we should do is At first initial position we should calculate flux, and final position we should calculate flux. We should find the change in flux divided with 0.25 seconds, that is the time interval. Then we will get EMF, and EMF by 2 ohm, that is the resistance, will get the current. Estimate the magnitudes of EMF and current induced in the coil. Horizontal component of Earth's magnetic field is approximately 3 into 10 power minus 5. Okay, we needed the value B, so we got it. And solution: initial flux through the coil, initial flux BA cos theta, cos 0 degrees, initially it is 0 degrees, therefore it is 3 pi into 10 power minus 7 Weber. And when it is rotated 180 degree, the theta will become 180 degree anti-parallel. At such an instance, cos 180 degree is minus 1. The magnitude will be same, but the values will be plus 3 pi into 10 power minus 7 and minus 3 pi into 10 power minus 7. And when we subtract them or we find the difference, it will become 3 pi into 10 power minus 7 minus of minus 3 pi into 10 power minus 7. So we will get it as 6 pi into 10 power minus 7. And they have mentioned that the area, there are number of terms, that is 500. So we'll get approximately the EMF induced to be 3.8 into 10 power minus 3 volt, or 3.8 millivolt. And when we divide it by 2 ohms, that is resistance, we will get current, that is 1.9 milliampere. Note that the magnitudes of E and I are the estimated values. We did not take the value of the Earth's magnetic field BH correctly, so they are indeed estimated values. Their instantaneous values are different and depend upon the speed of rotation at the particular instant. This is assumed at the average. These values are average values. At certain speed, there is a higher EMF produced depending on the flux change and depending on the speed, but this is only the average value. Now let's go to the next topic, that is Lenz's law and conservation of energy. Lenz's law and conservation of energy. In 1834, German physicist Heinrich Friedrich Lenz, that is 1804 to 1865, deduced a rule known as Lenz's law, which gives the polarity of the induced EMF in a clear and concise fashion. The statement of the law is: the polarity of induced EMF is in such a way that it tends to produce a current which opposes the change in magnetic flux that produced it. Okay, let's see here. Let's see this. This is a magnet, and we are pushing this magnet towards the coil. And when there is a change in magnetic flux, there will be a current induced in this coil, but this current will be in this direction. And if we use the right hand thumb rule, we will get that the uh, pole induced in this side is the north pole. The magnetic field in this side will be the north pole. As we know, uh, a current carrying circular loop acts as a bar magnet, and it also has poles, that is the north and the south poles. And due to this change in magnetic flux that is produced by the movement of this bar magnet toward this coil, it will produce a north pole. And we know that north pole get repelled. So basically this current which was produced by this movement of the magnet will oppose this movement that produced it. And in a similar way, when let's assume it is very near to the coil and this magnet is moving away from the coil, in such a case this direction of the current induced will reverse and it will form in this direction. Again, if we use the right hand thumb rule, we will get the direction of the magnetic field, and this pole is the south pole. South pole is produced in this direction. And we know that north pole and south pole get attracted. So This is restricting the movement this side. This created current, which will create a pole, a polarity, this will oppose the magnet from moving and creating a flux, change in flux. That is a law statement. As for why this happens is because of conservation of energy. If there was no opposition, the work done in moving this magnet from here to here would be zero. And that is and but the current produced, for us to produce current in this coil, there is need to be finite amount of work to be done. But if there is no opposition here, the work done will be zero. That is not possible. As such, there will indeed be opposition here to conserve energy. In 1834, German physicist, which gives polarity of the induced EMF in a clear, concise fashion. The statement is the polarity of induced EMF, polarity meaning north and south pole, of this induced EMF is in such a way that it tends to produce a current which opposes the change in magnetic flux that produced it. The negative sign shown in Faraday's law, that is E which is equals to minus d phi b by dt, this here negative sign here represents this effect as it is in the opposite direction. We use a negative sign here. We can understand Lenz's law by examining experiment 6.1, that is the magnet coil experiment. Section 6.21, in figure 6.1, we see that the north pole of a bar magnet is being pushed towards the coil. As the north pole of the bar magnet moves towards the coil, the magnetic flux through the coil increases. Hence, the current is induced in coil in such a direction that it opposes the increase in the flux. This is possible only if the current in the coil is in a counterclockwise direction with respect to the observer situated on the side of the magnet. Note that the magnetic moment associated with this current has north polarity towards the north pole of the approaching magnet. Similarly, if the north pole of the magnet is being withdrawn from the coil, the magnetic flux through the coil will decrease. To counter this decrease in magnetic flux or change in magnetic flux, the induced current in the coil flows in clockwise direction and its south pole faces this receding north pole of the bar magnet. This would result in an attractive force which opposes the motion of the magnet and the corresponding decrease in flux. What will happen if an open circuit is used in place of a closed loop in the above example? In this case too, an EMF is induced across the open ends of the circuit. The direction of the induced EMF can be found using the Lenz law. Consider figure 6.66, this figure here. A and B, they provide an easier way to understand the direction of the induced currents. Note that the direction shown here indicate the direction of the induced currents along with the poles. And where is this one here? And what there's a statement here. We use a closed loop here, right? Instead of that, in a case where we use an open circuit, it's an open circuit, it's not a closed loop. In this case, that is the open circuit as well, an EMF is induced across the open ends of a circuit. There is an EMF induced in the open ends of the circuit, and the direction of the induced EMF, using Lenz's law, we can find the direction. A little reflection on this matter should convince us on the correctness of Lenz's law. Suppose that the induced current was in the direction opposite to the one depicted in figure 6.6a. Instead of north, it created a south pole. In that case, The south pole, due to the induced current, will face the approaching north pole of the magnet. The bar magnet will then be attracted towards the coil at an ever increasing acceleration. A gentle push on the magnet will initiate the process, and its velocity and kinetic energy will continuously increase without expending any energy. That is energy. If this can be happened, one could construct a perpetual motion machine by a suitable arrangement. This violates the law of conservation of energy and hence cannot happen. That's what they said. Now consider the correct case shown in figure 6.6a. In this situation, the bar magnet experiences a repulsive force due to the induced current. Therefore, a person has to do work in a moving magnet. Where does the energy spent by the person go? This energy is converted into current. This energy is dissipated by the joule heating produced by the induced current. Basically, the work done by the current. If we put this current, the current induced in through a resistance, through like a bulb, by turning the bulb on, the person's mechanical energy, muscle power, by moving the magnet forward and backward, was automatically converted into current, and this current did some work through the bulb's resistance, and that is the Joule's law of heating, and produced light. Example 6.4. Here 6.7 shows a planar loops of different shapes moving out of or into a region of magnetic field which is directed normal to the plane of the loop, away from the reader. Determine the direction of the induced current in each case using the Lenz's law. Okay. Okay, there's a planar loops. These three loops which is here, 1, 2, and 3, they are planar loops, meaning they are in the plane of the paper or the book. They are moving into or out of this specific region. This region here is a region of uniform magnetic field, and there are this loop, the first one is moving into this region. This one and this one are moving out of the region. Now they are asking direction of induced current in each of the loop, that is using Lenz's law. Solution: the magnetic flux through the rectangular loop ABCD magnetic flux through the rectangular loop ABCD increases because it is coming from a no magnetic field region to the magnetic field uniform magnetic field region. Obviously the flux should increase. Due to the motion of the loop into the region of magnetic field, the induced current must oppose the flow along the path BCDAB so that it opens the increasing flux. It opposes the increasing flux. Okay. Since this is the flux is increasing, the flux is increasing when it's going from here, and assuming this is going inside, so the field lines should, from the perspective of this loop, should be north pole. So since it is going in, this should also create a north pole. To create a north pole, then the current must flow in this direction. Now this one, the next one, it is ABC. It is moving out of the magnetic field region. To oppose this, a current should be produced. If this was north again for this as well, to oppose this from going out of the region, it should create a south pole to create attraction. If that was the case, using the right hand thumb rule, you will get the direction to be this way. This is the direction of current. This is the direction of current. Now, as for this one, here as well, with respect to the loop, the magnetic field should be a north pole, and as it is reducing in flux, it should also create a south pole. And according to the right hand thumb rule, if it needs to create a south pole, then the current should be flowing in this direction. The magnetic flux through the rectangular loop ABCD increases due to the motion of the loop in the region of the magnetic field. The induced current must oppose the flow along the path BCDAB, the mentioned direction I did, the one I mentioned, that it opposes the increasing flux. Due to the outward motion, magnetic flux through the triangular loop ABC decreases, due to which the induced current flows along BACB, this direction here, like this, what I mentioned. As the third case, as the magnetic flux decreases due to the motion of the irregular shaped loop ABCD out of the region of magnetic field, the induced current flows along CDABC, so in this direction here. So it creates a south pole, oppose the change in flux. Note that there are no induced current as long as the loops are completely inside or completely outside the region of the magnetic field. Because it's a uniform magnetic field, let's assume there is a square here, a square loop here, and no matter where we move this inside this region of the uniform magnetic field, inside this square region of the uniform magnetic field, there is no current induced in this circular loop, that is, I mean the square loop. That is what they're saying here. Just because it is moving out of the loop, only that is the reason it is experiencing a induced current. And that is also an example why it is hard to create magnetic field when you move a loop on earth. There is magnetic field on earth, it is uniform. Because of that reason, when you move a loop high as well without any magnet near it, there will be no current produced. Now let us go to the next example. 6.5. A closed loop is held stationary in the magnetic field between the north and south poles of two permanent magnets held fixed. There is a closed loop is held stationary in the magnetic field between the north and the south poles of the two permanent magnets held fixed. Okay, there are two permanent magnets and there's a closed loop held between those permanent magnets. I mean the north and the south pole faces of these two magnets. Can we hope to generate current in the loop by using very strong magnets? Okay, next question. A closed loop moves normal to the constant electric field between the plates of a large capacitor. Is a current induced in the loop when it is wholly inside the region of the capacitor plates. When it is partially outside the plates of the capacitor, the electric field is normal to the plane of the loop. Now, third question. A rectangular loop and a circular loop are moving out of a uniform magnetic field region to a field-free region with constant velocity v, in which loop do you expect the induced EMF to be constant during the passage out of the field? The field is normal to the loops. Okay, first question. There's a closed loop. It is held stationary in the magnetic field between north and south poles of two permanent magnets. And they are asking, can we hope to generate current in the loop by using very strong magnets if it's held stationary? No. Okay, there's also a D question. We'll read that later. No. However strong the magnet may be, current can be induced only by changing the magnetic flux of the loop, not by stationary. Second question. A closed loop moves normal to the constant electric field between the plates of the large capacitor. There is a capacitor, electric field like this, current loop like this, electric field lines passing like this. Normal to the constant electric field between the plates of a large capacitor is a current induced in the loop when it is wholly inside the region between the capacitor plates and it is partially outside the plates of the capacitor. The electric field is normal. Let's see the answer. No current is induced is induced in either case. Current cannot be induced by changing the electric flux. It can only be induced by changing the magnetic flux. Okay, that's important to remember because it is confusing. Now the third question, a rectangular loop and a circular loop are moving out of a uniform magnetic field region. There are two loops. One is a rectangular loop here, one is a circular loop. They are moving out of a magnetic field, uniform magnetic field region to a free region with a constant velocity v. In which loop do you expect the induced EMF to be constant during the passage out of the end region? The field is normal to the loops. The induced EMF is expected to be constant only in the case of the rectangular loop. In the cases of the circular loop, the rate of change of area of the loop during the passage out of the field is not constant. Hence, induced EMF will vary accordingly. Okay, as the question is, as this is going out of the region of the uniform magnetic field, the induced EMF will be constant in which of the cases? The answer is this case. As for y, let's assume this is out of the region. This part is out of the space, and this is inside. As it is coming out, only this part, only this much is getting added on. It is a constant amount of area, same as before for unit time interval. Because of that, the EMF will remain same. But assume here this area and this area. If we consider this area and this area, obviously this area is much higher than this area. So the magnetic flux, the EMF will increase here because the area increased, as it is dependent on the magnetic flux, and magnetic flux is again dependent on the area. Now let's see the fourth question. Predict the polarity of the capacitor in the situation described by figure 6.9. There is two magnets here. This is the south north, it's moving towards this direction, and if that was the case, it should create a force to oppose this south pole, meaning it should create a south pole. To create a south pole, According to the right hand thumb rule, it should be current should flow in this direction, and since the north is moving this side, to oppose this again, there should be a north pole in this side. Since this is south, that side is obviously north, so both will induce a current in this direction. And if that was the case, then A plate will be positive, B plate will be negative. A will be positive and B will be negative. Now let's go to the next topic, next main topic, that is motional electromotive force, motional EMF. Let us consider a straight conductor moving in a uniform and time independent magnetic field. Let's see the figure. The arm PQ is moved to the left, thus decreasing the area of the rectangular loop. This movement induces a current in current I as shown. Because the EMF is directly proportional to the change in magnetic flux, and change in magnetic flux is directly proportional to the change in area. EMF is directly proportional to the area, and because of that, it will cause a change in magnetic flux, and because of that, an EMF, a current, is induced, and the current is shown in the direction is shown here. Basically, this is a frame. It is a conducting frame. This is also conducting rod, and we are slowly moving this rod forward, so that what we are doing here is we are creating a changing area. We're changing the area. We're changing the flux. Figure 6.10 shows a rectangular conductor PQRS, in which the conductor PQ is free to move. The rod PQ is moved towards the left with a constant velocity V as shown in the figure. Assume that there is no loss of energy due to friction. There is no friction, let's assume. PQRS forms a closed circuit enclosing an area that changes as PQ moves. It is placed in a uniform magnetic field B, which is perpendicular to the plane of this system. Magnetic field, the crosses you see are magnetic field which are going into the plane of the book, meaning they are exactly perpendicular. The angle between the area vector and the magnetic field should be 0 degrees. If the length RQ, which is equals to S, and the movable rod is L, the magnetic flux phi B enclosed by the loop PQRS will be BLX. Basically, magnetic flux is which is equals to B times A, and A is area of a rectangle, which is equals to breadth times length, or length times breadth, and length is this one, that is X, and breadth is this one, XL. So basically it became BLX or BXL. Since X is changing with time as we move forward, this distance, the length is keep on reducing, is changing with time. The rate of change of flux will induce an EMF, that is minus d dt by BLX. Since B, that is magnetic field, and L, the length of the rod, this rod will remain constant. Only variable is the X, that is breadth. Everything except breadth will come out. It will become BL dx by dt, and we know that displacement by time, which is velocity. So the final formula EMF induced is PLV. Where we have used dx by dt is equals to minus V, which is the speed of the conductor PQ. The induced EMF BLV is called motional EMF. Thus, we are able to produce induced EMF by moving a conductor instead of varying the magnetic field. That is, by changing the magnetic flux enclosed by a circuit. We saw that EMF can be induced by altering the shape of the conductor, and this is basically the direct application of that. It is also possible to explain the motional EMF expression in equation 6.5 by invoking a Lorentz force acting on a free charge carriers of conductor PQ. It is also possible to explain the motional EMF expression in EQ by invoking the Lorentz force acting on the free charge carriers of the conductor. Consider any arbitrary charge Q in the conductor PQ. PQ must be this rod. This moving rod is PQ. Let's assume there is current passing through and there is a charge Q in the conductor which is moving. It moves with a speed v. The charge will also be moving with a speed v in the magnetic field B. The Lorentz force on this charge is QEB sine theta in magnitude because sine theta is 90 degrees. This is the angle between velocity and magnetic field, not area and magnetic field. Area vector and magnetic field angle is 0 degree, but velocity in this case and magnetic field should be 90 degrees. So that sine 90 is 1 and it will become QEB in magnitude and its direction is towards Q. All charges experiences the same force in magnitude and direction irrespective of their position in the rod PQ. All charges will experience the same force, that is Lorentz force, in magnitude and direction. The work done in moving charge from P to Q is W equals Q delta V, change in potential, that is QVBL. Since EMF is the work done per unit charge, dividing this will get work done is equals to BLV. This equation gives the QVBL. Okay. Okay, QEB is the force experienced by the charge. Every charge will experience QEB is the force. W equals force into displacement or distance, force into displacement, and force which is Lorentz force here is QEB sine theta or QEB. Force is QEB and distance is the length of the rod. So work done is equals to QEB times the length of the rod, that is L. So we get the equation W is equals to QEBL, and we know this formula that potential is the work done in moving a unit charge from one place to another. Therefore, potential which is work done by charge, and when we divide this by charge, we will get BLV, that is our EMF value. This equation gives EMF induced across the rod EQ and is identical to equation 6.5, we stress that our presentation is not wholly rigorous, but it does help us understand the basis of Faraday's law when the conductor is moving in a uniform and time dependent magnetic field. On the other hand, it is not obvious how an EMF is induced when a conductor is stationary and the magnetic field is changing, a fact which Faraday verified by numerous experiments. In the case of stationary conductor, the force on its charges is given by F, which is equals to Q. This is the Lorentz force equation, and since we are not considering magnetic field, it will only be QE. Since it's a stationary conductor, as such velocity we take it as 0. Thus any force on the charge must arise from the electric field term E alone. Therefore, to explain the existence of induced EMF, the induced current, we must assume that a time varying magnetic field generates an electric field. However, we hasten to add that electric fields produced by static electric charges have properties different from those produced by time varying magnetic fields. In chapter 4, we learn that charges in motion can exert force torque on a stationary magnet. Conversely, a bar magnet in motion, or more generally a changing magnetic field, can exert a force on the stationary charge. This is the fundamental significance of the Faraday's discovery. Electricity and magnetism are related. Okay, let's read that again. This is similar to the third experiment that Faraday did. The third experiment was about turning a switch on and off. This creates a magnetic field without motion. How this works, he still didn't know. So to find that out, he then didn't know to find that out. He did many experiments. So let's see what NCERT gave here. It's not obvious how an EMF is induced when a conductor is stationary and the magnetic field is changing. Only the magnetic field is changing. A time varying magnetic field. A fact Faraday verified by numerous experiments in the case of stationary conductor. The force on its charges is given by F, which is equals to QE. The force on the charges, okay, thus any force on the charge must arise from the electric field term E alone. Therefore, to explain the existence of an induced EMF or induced current, for us to explain existence of an induced EMF or induced current, since there is only electric field, we must assume that what we are assuming, a time varying magnetic field generates an electric field. Uh, there is one conductor, two conductors, number one first conductor and second conductor. First conductor and second conductor are both fixed. Second conductor is producing a time varying magnetic field and it is not moving, and the force on its charges must be only due to electric field. In such a case, if there is a current induced in the first coil, that means that this time varying magnetic field produced by the second coil is somehow creating or inducing an electric field inside the first coil. However, we hasten to add that electric fields produced by static electric charges have different from those produced by time varying magnetic fields. We know that static charges produce electric field. A region surrounding the electric field, the static charge is called is having an electric field. It's the electric field region where we experience electric force. Okay, and this electric force produced by static charges, electric field produced by static charges, is having different properties from those produced by time varying magnetic field. Time varying magnetic field is different from this electric charges static field. And in chapter 4, we learn that charges in motion, that is current, this can exert a force or torque on a stationary magnet. This is due to the induced magnetic field. Conversely, a bar magnet in motion or generally a changing magnetic field can exert a force on a stationary charge. This also we know because we saw the QEB formula. QEB sine theta, the force experienced on a moving charge from a magnetic field. Just like how a current will give force on a magnet, a moving charge will also experience force due to a magnetic field or magnet. And this relation is a fundamental significance of Faraday's discovery. Electricity and magnetism are related. Example, a metallic rod of 1 meter length is rotated with a frequency of 50 revolutions per second. A revolution is a 2 pi radians per second. This is angular velocity given. 100 pi revolution per second. 100 pi radian per second, not revolutions. With one end hinged at the center and the other end at the circumference of circular metal ring of radius 1 meter. About an axis passing through the center and perpendicular to the plane of the ring, a constant and uniform magnetic field 1 Tesla parallel to the axis is present everywhere. What is the EMF between the center and the metallic ring? Okay, let's see the question once more. There is a metallic rod having length of 1 meter and its frequency, angular frequency, is 50 revolutions per second. And arrangement is one end of this metallic rod is hinged at the center of the circular metallic ring, and the other end at the circumference. It's acting like a radius of radius 1 meter, exactly 1 meter radius. So it covered up, acting as a radius. About an axis, it is rotating about an axis passing through the center and perpendicular to the plane of the ring. Okay, and there is a magnetic field 1 Tesla parallel to the axis everywhere, meaning it's going to the plane of the paper. Let's see the diagram. This one is the metallic rod. It is acting as the radius, metallic ring. They're asking what is the EMF between the center and the metallic ring, potential difference between the center and the metallic ring. As the rod is rotated, free electrons in the rod move towards the outer end due to the Lorentz force and get distributed over the ring. As we see that the ring is getting rotated, free electrons that are in the rod will move out and will get settled in the ring, thus resulting the separation of charges produces an EMF across the ends of the rod. At a certain value of EMF, there is no flow of electrons. As this electrons goes from this rod to the outer ring surface, this will create a potential difference due to the motion. These electrons will flow to the outer ring till the potential difference becomes zero. At certain value of EMF, there is no more flow of electrons and a steady state is reached. Using equation 6.5, the magnetic field of the EMF generating across the length dr of the rod as it moves at right angles to the magnetic field is given by, okay, the magnitude of the EMF generated across a length dr of the rod as it moves at right angles to the magnetic field. D epsilon, which is EMF, which is equals to BVL or BVDR. dr is a small radius element. It is given by this, and for total we need to take integration from 0 to r. We will get the formula as b omega r square by 2. After integration, we have used velocity is equals to omega r. This is better since we don't know the actual linear velocity. We know the angular velocity but not linear velocity, and substituting this we will get 157 volt. This is the first method. Okay, now second method is to calculate the EMF. We can imagine a closed loop OPQ in which the point O and P are connected with the resistor R and OQ is the rotating rod. Okay. Let's see the diagram. OPQ is a circle, is a closed loop in which O and P are connected with a resistor R. O and P are connected with a resistance R, and OQ is the rotating rod. OQ is the rotating rod. The potential difference across the resistor is then equal to the induced EMF the potential difference across the resistor, that is OQ, okay, OP, is then equal to the induced EMF, and it is also equal to B times the rate of change of area of loop. If theta is the angle between the rod and the radius of the circle at point P at time t, the area of the sector OPQ is given by this formula, pi r square into theta by 2 pi, half r square theta, where r is radius of the circle, hence induced EMF is, once again substituting the formula, this is the area of the sector. Then B value we know, BA cos theta is the total magnetic flux, change in magnetic flux. We can use Faraday's law and we will get finally half dr square d theta by 2, or d theta by dt, and d theta by dt is omega, that is angular frequency. Therefore we will get it as b omega r square by 2, the same as the prior equation, b omega r square by 2, and thus same answer, 157 volt. Now next is example 6.7. A wheel with 10 metallic spokes, each 0.5 meter long, is rotated with a speed of 120 revolution per minute in a plane normal to the horizontal component of Earth's magnetic field at a place if HE horizontal Earth's magnetic field is equal to 0.4 G at the place, what is the induced EMF between the axis and the rim of the wheel? Note that 1 G is equals to 1 G, basically 1 Gauss, 10 power minus 4 Tesla. Okay, let's read the question again. A wheel with 10 metallic spokes. There is a wheel, it has a metallic spokes. They are of 0.5 meter long and it's rotated with a speed of 120 revolution per minute. This is angular speed or angular velocity in a plane normal to the horizontal component. Horizontal component, normal to the horizontal component meaning, okay, and the Earth's magnetic field is 0.4 Gauss at that place. What is the induced EMF between the axis and the rim of the wheel? Induced EMF from the prior formula, which is equals to omega b r squared by 2, and we will get it as 6.28 into 10 power minus 5 volt. Simple formula substitution. The number of spokes is not required because the EMF across the spokes are in parallel. Now let's go to the next main topic, that is inductance. An electric current can be induced in a coil by flux change produced by another coil and its vicinity, or flux change produced by the same coil. Okay, they're saying that an electric current can be induced in a coil by flux change produced by another different coil or the flux change produced in the same coil. These two situations are described separately in the next two subsections. However, in both the cases, the flux through a coil is proportional to the current, that is phi b, which is directly proportional to the current. Further, if the geometry of the coil does not vary with time, then the change in flux is directly proportional to the change in current. For a closely wound coil of n turns, the magnetic flux is linked with all the turns. When the flux, the phi b, through the coil changes, each turn contributes to the induced EMF. Therefore, a term called flux linkage is used, which is equal to n phi b for closed wound, and in such a case n phi b is directly proportional to I. A constant of proportionality in this relation is called as inductance. We shall see that inductance deeply only on the geometry of the coil and intrinsic material properties. This aspect is akin to capacitance, which for a parallel plate capacitor depends on the plate area and plate separation and dielectric constant K of the intervening medium, intrinsic material property. Inductance is a scalar quantity. It has dimensions, this one, given by the dimensions of flux divided by the dimensions of current. The SI unit of inductance is Henry and is denoted by H. It is named in honor of Joseph Henry, who discovered electromagnetic induction in USA independently of Faraday in England. Okay, let's see that again. Inductance is the heading. An electric current can be induced in a coil by flux change produced by another coil in its vicinity, or flux change produced by the same coil. These two situations are described separately. Okay, in both the cases, the flux through the coil is proportional to the current That is, higher the flux, higher the current, or higher the change in flux. And assuming that the geometry of coil should not change, as the flux decreases, the current decreases, and the rate of change of flux increases, then the current shall also increase. Okay. As for why, it depends on the geometry of the coil. What if the coil reduced in area? That will reduce area, therefore change flux and change current as well. Then for a closed coil wound of n turns, the same magnetic flux is linked with all the turns. All the turns will have the same magnetic flux, and the flux B through the coil changes. Each turn contributes to the induced EMF. Let's assume this flux is changing, then each turn contributes to the induced EMF. Okay, we are talking about self-inductance here. In case of self-inductance, if there is a change in flux in, then if there is a change in flux, since that is linked in a closely wound coil, the flux is linked and each turn will have the same flux. As if there is a change in the magnetic flux, then all the turns will experience the change in magnetic flux, due to which there will be an EMF produced in each and every turn, therefore contributing to the whole, uh, each turn contributing whole for the EMF change or EMF induced. That's what they mean by that. Therefore, because of that, a term called flux linkage is used, which is equals to N phi B, the total flux through all the coils, for a closely wound coil. In such a case, N phi B is directly proportional to I. We saw that higher the flux, that is higher the I for a single turn coil. Here, since because all the coils have the same flux, we don't need to complicate it, and therefore we have N phi B, which is directly proportional to I. The constant of proportionality in this relation is called as inductance. Basically, phi B, which is directly proportional to I, phi B, which is equals to Li, and L, which is equals to phi B by I, where L is called as inductance and it is the proportionality constant. The constant of proportionality in this relation is called as inductance. And if we see that, we shall see that inductance depends only on the geometry of the coil and intrinsic material properties. Okay, like how can we say what does this L depend on? L is directly proportional to the flux. Flux depends on area of the coil, that is geometry of the coil. Magnetic field doesn't matter right now, and it also depends, or it might depend on the magnetic field as well. The flux depends on the magnetic field, and magnetic field produced, as for how much magnetic field is produced, depends on the intrinsic properties of the material used. If the coil used is a material which produces strong magnetic field, then the flux change will also be high, therefore producing high deflection or high current. And it depends only on the geometry of the coil And intrinsic material depends on two things, that is geometry of the coil, that is number of turns, area of the coil, and intrinsic material properties. The aspect is akin to capacitance, which for a parallel plate capacitor depends on plate area and plate separation, geometry, and dielectric constant K of the intervening medium, intrinsic material property. This is like similar, this inductance, just like capacitance. Like for a parallel plate capacitor, if we take, the capacitance doesn't depend on charge voltage or anything like that. It depends on the geometry of the capacitor, like the distance between the basic the plate separation, the area of the plates, the material dielectric used between them, the dielectric constant, etc. It does not depend on anything other than that. Similarly, this inductance as well depends on the geometry of the coil, the number of turns of the coil, the material used for the coil, etc. And the dielectric constant K. Okay, inductance is a scalar quantity. It's a scalar quantity. It has dimensions because phi is scalar, I is also scalar, current and flux is scalar. So this one is also scalar. Inductance is scalar. It has the dimensions ml square t power minus 2, same as energy, but there is a current square below. That's all. Given by the dimensions of flux divided by the dimensions of current. The SI unit of inductance is Henry and denoted by H. The unit of this one is Henry or Weber per ampere, or Henry, we can say Henry, and is denoted by H. It is named in honor of Joseph Henry, who discovered electromagnetic induction in USA independently of Faraday in England. Okay, let's go with the next subtopic, that is mutual inductance. Mutual inductance, consider figure 6.12. Let's see the figure. Two long coaxial solenoids of the same length L. Two solenoids. This is one solenoid having N1 turns. This is one more solenoid having N2 turns. They have coaxes, meaning their centers are aligned, or concentric, having the same center, having the same axis. That is what they mean. They have a length L. R1, R2 are the individual radius. S2 might be the surface area, and S1 also might be the surface area. Okay, that is the surface. That is a diagram. This is the figure 6.12, which shows two long coaxial solenoids, each of length L. We denote the radius of the inner solenoid S1 by R1, and the, just a minute, Okay, then let's continue. It was a longer break than expected, but mutual inductance, the diagram which we saw before, which shows two long coaxial solenoids, each of length L. We note the radius of the inner solenoid S1 by R1 and the number of turns per unit length by N1. The corresponding quantities for the outer solenoid S2 and R2 and N2 respectively. Let N1 and N2 be the total number of turns of coils S1 and S2 respectively. When a current I2 set up through S2, it turns it in turn sets up a magnetic flux through S1. Let us denote it by phi 1. The corresponding flux linkage with solenoid 1 is N phi 1, which is equals to M12 I2, where M12 is called the mutual inductance for solenoid S1 with respect to solenoid S2. It is also referred to as the coefficient of mutual induction. For these simple coaxial solenoids, it is possible to calculate M12, the magnetic field due to the current I2 in S2 is mu naught N2 I2. The resulting flux linkage with coil S1 is N1 phi 1, this formula here, and you will get that mu naught N1 N2 pi R1 square I1 I2, where N1L is the total number of turns in solenoid S1. Thus, from equation 6.7 and 6.8, we get that the mutual inductance, which is equals to mu naught N1 N2 pi R square 1 L. Well, let's read that again. There are two long coaxial solenoids. The length of each solenoid is denoted by L. They have the same length. We denote the radius of the inner solenoid. S1 and S2 are the solenoids, and the inner solenoid S1 has a radius of R1. And the number of turns per unit length, that is capital N by L, for the first solenoid is N1, and the corresponding quantities for the outer solenoid S2, where R2 is the radius of the second solenoid, N2 is the number of turns per unit length of the second solenoid. Then let capital N1 and capital N2 be the total number of turns of coils S1 and S2. Small n are total number by L, that is length. When a current I2 is set up through the coil through the solenoid S2, it in turn sets up a magnetic flux through S1 when there is a current flowing through the S2 solenoid. Because it's the function of the solenoid is to create parallel strong magnetic field inside the solenoid, there will be magnetic flux created for the solenoid S1. And we saw that inductance, which was directly proportional to current, so N phi B, which is directly proportional to I, and N phi B, which is equals to Li. And in this case, we instead of taking L, we take it as M12, where it is a proportionality constant. N1 phi 1 is equals to M12 I2. The flux inside the first solenoid is directly proportional to the current in the second solenoid. M12 is called the mutual inductance of solenoid S1, or we can just call the inductance of the solenoid S1, and it depends only on the geometry of the solenoid, number of turns, and the material it was made of. M12 is the mutual inductance of solenoid S1 with respect to solenoid S2. It is also referred to as the coefficient of mutual induction. For these simple coaxial solenoids, it is also possible to calculate M12. The magnetic flux due to the current I2 in S2 is mu naught n2 I2. This is the basic formula, that is the magnetic field B which inside a solenoid mu naught Ni. That is the formula. This is for the magnetic field inside the second solenoid. Then the magnetic flux, resulting flux linkage with coil S1 is N phi 1, which is equals to number of turns N phi 1 is equals to total number of turns in this solenoid, area, and this is magnetic field. The total flux with each of these is mu naught n1 n2 pi r1 square. Okay, where n1l is the total number of turns in solenoid 1. Okay, this is from equation this is resulting flux linkage. So the flux linkage is this one. Then okay, I'll leave that be for now. This is M12. We got it as, we need to find M12, that is mutual inductance. Okay, we know that the value of is, okay, this is the main equation. We know this equation through the inductance relation from the before paragraph. And just if we go here inward, n1, let's go down, n1 phi 1, which is equals to m12 I2, and phi 1 we know the value, phi 1 we know the value, it is BA cos theta cos 0, which is equals to 1. And magnetic field inside the solenoid, which is equals to mu naught Ni, which is due to the second solenoid, which is mu naught N2 I2, because this magnetic field due to the second solenoid, there is no current in the first solenoid, it is solely due to the second solenoid. And filling in this equation, we need area of the first solenoid, and area which is equals to pi r1 square, and phi, which is not BA but NBA, this is flux 1, which is equals to N1BA. Number of turns in the first coil. Now finally substituting in this equation, we will get it as, now N1 we can write as N1 times n length L. We will get phi 1, which is equals to Wait a second. We are having already n1 from the main equation, n151, which is equals to n1ba. n151 which is equals to n1ba. From this equation we will get n151, the value we want. We will get it as n1l. We are writing this n1 here as n1l. We just multiplied n1 both sides to get our equation, desired equation, to substitute in this equation. This is the main equation. We are finding m12 value. To get m12 value, we need to first find n151 value. To do that we are finding the n151 value. Now to get the n151 value, we have all the individual values. That is n1 value, that is n1l, and b value inside a solenoid. This is the value, and area, which is pi r1 square. So n1l1 mu naught n2i2 pi r1 square. Totally we'll get n151 value to be equal to mu naught n1 n2 pi r1 square n1 over n2 over r1 square over mu naught over L and I2 are not over. L, I2. This is the value of n151. Now substitute this in the main this equation. We got the n151 value, substitute it here. We will get it as mu naught n1 n2 pi r1 square shift it here. Okay, r1 square li2, which is equals to m12 i2 i2 cancel. m12 value will get as mu naught n1 n2 pi r1 square. This is the mutual inductance value. That is what they have mentioned in the textbook. Note that we neglected the edge effects, like the edge of the solenoid. We considered it as an infinite solenoid. The magnetic field mu naught n2i2 to be uniform throughout the length and width of the solenoid S2. This is a good approximation to keep in mind that the solenoid is long, implying that length is much greater than the radius. We now consider the reverse case. A current I1 is passing through the solenoid S1, and the flux linkage with coil S2 is N252, which is equals to M21 I1. M21 is called the mutual inductance of S2 with respect to solenoid S1. The flux due to current I1 in S1 can be assumed to be confined slowly inside S1 since the solenoids are very long. Thus, flux linkage with solenoid S2 is N252, which is N2L pi R1 square mu naught N1 I1, where N2L is the total number of turns of S2. M21, which is equals to mu naught N1 N2 pi R1 square L. Equations 6.9 and 6.10, we say that M12, which is equals to M21 MC. Okay, let's see the second case scenario as well. First, we took mutual inductance of S solenoid S1 with respect to S2. Now we take solenoid S2 with respect to S1, that is M21. If that is the case, then we take N252, that is the number of turns and flux inside the second coil, which is equals to M21 I1, since current is only in the first solenoid this time. M21 is called a mutual inductance of solenoid 2. Okay, and the flux density to the current I1 in S1 can be assumed to be confined solely inside S1 since the solenoids are very long. Flux linkage with solenoid S2 is N252. Okay, same thing, but here we take the second solenoid's number of turns N2. Then this is area of the first coil because the current is solely confined in the first coil. Maybe they are taking it as an approximation to get the same answer. And mu naught N1 I1, that is the magnetic field inside the first solenoid. We will get M21 from this approximation. We get M21 to be equal to M12. We have demonstrated this equality for long coaxial solenoids for long, infinitely long coaxial solenoid. However, the relation is far more general. Note that if the inner solenoid was much shorter than and placed well inside the outer solenoid, then we could still have calculated the flux linkage N151 because the inner solenoid is effectively immersed in a uniform magnetic field due to the outer solenoid. In this case, the calculation M12 would be easy. If it was a short solenoid and the radius of R1 was much smaller than the second solenoid, we could have easily calculated M12, that is the magnetic flux, I mean the inductance with the first solenoid of the first solenoid with respect to the second solenoid. That would have been easy. But it would be extremely difficult to calculate the flux linkage with the outer solenoid as the magnetic field to the inner solenoid would vary across the length as well as across the section of the outer solenoid. The magnetic field lines inside the like the outer solenoid will be concentrated inside and will be easily, and it will be uniform parallel inside, and the solenoid having the smaller radius will have uniform magnetic field due to the second solenoid. But the first solenoid being smaller, if it was the one carrying the current, it cannot create uniform magnetic fields for the outer solenoid. Because of that, to calculate the mutual inductance in such a case will be hard. Therefore, the calculation of M21 would extremely 1 minute. The calculation of M21 would be extremely difficult in this case. The equality M12 M21 is very useful in such situations. We explained the above example with air as the medium with solenoids. Instead, if a medium of relative permeability mu r had been present, we just write the mutual inductance would be mu r mu naught N2 N1 pi R1 square L. It is also important to know that the mutual inductance of a pair of coils, solenoids, etc. depends on their separation as well as their relative orientation. Let us see example 6.8. Two concentric circular coils, one of smaller radius R1 and the other of larger radius R2, such that R1 is much smaller than R2, are placed coaxially. In this case, we are easily able to calculate M21. Wait, it is no, it is M12. We can easily calculate M12, but we cannot easily calculate M21 because the radius disparity between them is very high. Are placed coaxially with centers coinciding. Obtain the mutual inductance of the arrangement. Solution: let I be the current flowing through the outer circular coil. The field at the center of the coil is B2, which is equals to mu naught I2. Since the other coaxial placed over the coil by R2. B2 is equals to mu naught I2 by 2R2. Since the other coaxially placed coil has very small radius B2, may be considered constant over its cross-sectional area. Hence, pi 1, which is equals to pi R1 square B2 mu naught pi R12 square by 2R2. We get this equation here, and M12 I2, thus M12 which is equals to mu naught pi R1 square by 2R square. If we consider them to be equal, then we will get same for both of them. Not sure why we got B2 which is equals to mu naught I2 by 2R2. There's why there is a division of 2R2 there. But somehow we got that, and we just substituted the values here. Since it is a single turn coil, there is no turns. It's a circular coil and it only has one turn, so n will become automatically 1. So the formula is much simpler with being BA, phi 1 which is equals to BA. We will get it as M12, and since this is the value we got and I2 is out, phi 1 should be equal to M12 I2. Thus M12 will become this, and for R1 much smaller than R2, both will be equal. Now let us recollect experiment 6.3, that is the turning switch on and off. Section 6.2 is in that experiment, EMF is induced in the coil whenever there was a change in current through the coil C2. Let's phi 1 be the flux through the coil C1. Say N1 turns when current coil C2 is I2. Then from equation 6.7 we have this one for currents varying with time. Both are flux densities, I mean flux, change in flux. So since this is number of turns which doesn't have a unit, both will have the units of flux itself. In such a case, we can take both as flux, since induced EMF in the coil is given by this. This is the basic Faraday's first law formula, and we know this is directly equal to this one. Replace that one with this one, and we will get E1 which is equals to mutual inductance di2 by dt. It shows that varying current in a coil can induce EMF in a neighboring coil. The magnitude of the induced EMF depends upon the rate of change of current and mutual inductance of the two coils. With that, I will be ending today's stream. See you later.